Okay, so I hope by this time that you're comfortable with the concept of a z-score. A z-score tells us how many standard deviations away from the mean a score is. And we can use it, it's called a standard score, because I can compare people or fish or temperatures or whatever data I'm looking at. I can compare different distributions. I can compare people that are from different distributions with different parameters by looking at their z-score and doing that comparison. So people from disparate distributions can be compared one to another by identifying their location within a distribution. That is, where they are relative to everybody else. Because what we're doing, here's our z-score formula again, okay? And what we're doing is we're saying, how does this score compare to the mean? That is, how does this score compare to the average of everyone? And this is our deviation. And then how does the deviation compare to the average deviation for the entire distribution? Okay, so we're going to use this information, and it's going to become very powerful for us. We're starting to make our way to using statistical analyses for inferential statistics. Like, we're sort of on the cusp of descriptive and inferential, but using z-scores will be very powerful for us. And one of the reasons for that is because, like I've mentioned before, normal curves are ubiquitous. That is, they're very common. We see them all over the place, okay? They look something like that. Boy, I don't like that one. It looks like it's a little bit skewed. So I'm going to try to do it like this. Okay, that's better. All right, we know it's a symmetrical distribution, and remember there's an implied frequency axis here. But if we draw this down like this, right, we know that this will be the mean for our normal curve. And there are blocks under here, right? This is just a collection of blocks, the distribution at any given x value, right? Just to be complete here. But I'm assuming that you're with me with this. So this is a number line. This is our balance point, our mean. And we also know that not all the scores are the same. We have a certain standard deviation. Okay? The mean and the standard deviation are our gold standards for descriptive statistics. What I want to do now is, I don't have any values here, because if we're talking about a normal curve and this kind of shape and this kind of distribution, which I'm going to again say is ubiquitous, this is what many, many, many distributions look like. And I want to give you sort of a feeling for where one standard deviation away from the mean, where that is, or what it would look like, okay? And so I'm going to do something like maybe about here is one standard deviation away from the mean. And of course, if this is symmetrical, then this would be one standard deviation below the mean, right? It would be an equal amount, an equal distance, let's say, away from the mean. So this point represents the mean plus one standard deviation. And this point would be a score that's equal to the mean minus one standard deviation. Okay? And in fact, let's put this in terms of z-scores. Even though I don't have any specific values here, I certainly know what the z-score would be right here. Okay? I know what the z-score would be right there. And sometimes people are like, how the hell do you know what the z-score is going to be right there? Well, we have to remind ourselves of the conceptual meaning of the z-score. It's how many standard deviations away from the mean you are. If you are at the mean, then your z-score is going to be 0, okay? Because you're 0 standard deviations away from the mean. Okay, let's go out to this point. If this point represents the mean plus 1 standard deviation, then that means here my z-score is plus 1. I'm 1 standard deviation above the mean, so my z-score is plus 1. If we go down here, this is the mean minus 1 standard deviation. So in this case, I'm 1 standard deviation below the mean. My z-score is going to be minus 1. Okay? Now, let me just put the point here. This is true for any normal distribution. I mean, this is what it would look like. Whether the mean is 100 and the standard deviation is 10, or whether the mean is 72 and the standard deviation is 5, or whether the mean is 1,226 and the standard deviation is 307. This is what the graph would look like in each of those cases. That is, since the z-score is a normalized score, this is what it's going to look like. It gives us the position in the curve of a particular x value. Okay? Now, I also, we're going to start thinking about z-scores and normal distributions, and we're going to start to, we're going to end up converting these z-scores into percentiles. Okay? And what I want to do right now is ask you, I mean, if we consider the area under the curve as, if it's the entire curve, we'll talk about 100% of the area, right? 100% is the entire curve. What I would like you to do is to think about what the area underneath the curve would be, and that is just by visual inspection here, okay? Let's see if we can make some guesses about what the area underneath the curve would be to be, now listen carefully to this, to be within 1 standard deviation of the mean. Now when I say to be within 1 standard deviation of the mean, I'm not making a distinction of below or above, and so really I'm talking about this entire area. That is, this person is within a standard deviation of the mean. This person is within a standard deviation of the mean. This person is within a standard deviation of the mean. This person is within a standard deviation of the mean. What I would like for you to make a guess about is what percentage of the normal curve, and in this case, I can say what percentage of a normal curve, that is, any normal curve, would fall between a z-score of minus 1 and a z-score of plus 1. That is, what percentage of the curve falls within a standard deviation of the mean. Okay, everybody with me? Because the questions will be asked differently by different people. The questions will look differently depending on what problem you're trying to solve. And so we need to sort of be comfortable identifying this area. Okay, I could say what area falls between a z-score of minus 1 and a z-score of plus 1. That ends up sounding a little bit more mathematical than I would like. I would rather say, what percentage of the population falls within a standard deviation of the mean? That's what's shown here, okay? So what do you think? What do you think? Some of you might say 50%. Well, I would argue, I mean, if you look at the total area of the curve, 100%, I think that this looks like more than 50%. This looks like more than 50%. This one should maybe be a little bit further out here, right? Because these have to be equal. So other guesses, and I force students to guess in my class because I want you to look at it and make some guesses. Maybe 60%, right? Somebody might say 70%. I'm like, okay, maybe. If you said 90%, I'd be like, does this look like 90% of the whole? I think it's a little less than that, right? 60%, 65, 75, 70, 72. Okay, we can make a lot of guesses here. For purposes, a year from now when you're thinking about this, you don't have to be as exact as you are in this class. We'll get the exact value. But I'm going to tell you, it's about 70%. Okay? It's about 70%. That is, for any normal distribution, about 70% of the population falls within a standard deviation of the mean. Okay? About 70%. We're going to get much more detail, much more specific about that because it's not quite 70%. But that's a good number to have in your head, and it's a good number next year when people are talking about this. If you have a class or you're in an agency and they're talking about standard deviations, that's a good kind of approximation for what percentage is within a standard deviation. Okay? So, now I have another question. Knowing this, let me ask you this question, because this right here is an X. This person has a score of X, whatever that is, which is one standard deviation above the mean right here. Okay? Here's the next question. And I would not ask you to think about this if I didn't think that you could figure this out. It's not necessarily easy. It's not straightforward. But let me give you the question here. If somebody was at this score right here, what would be their percentile rank? That is, what percentile would they be at if they were right here in this distribution? Now, don't answer quickly. Don't answer quickly. And don't just make guesses in this case. In this case, it's figure outable. What would be your percentile rank if you were right here? Okay. The first thing you have to do when you answer this question, and this will be true for many questions to come in this class, is you have to sort of unpack the question. Oftentimes students get frustrated because they don't know the answer right away. And if you don't know the answer right away, you must not know the answer or be able to get the answer. And I think that that is kind of weird because I'm not asking you, for example, about what the capital of Pennsylvania is, right? If I ask you the capital of Pennsylvania, that's a kind of a question. You either know it or you don't know it, right? And it's Harrisburg, by the way. Some people would guess Pittsburgh or Philly, but the capital of Pennsylvania is Harrisburg. You kind of either know that or you don't. In these cases, the questions oftentimes are figure outable, but you have to sort of unpack the question. So let me repeat the question. And the question is, what percentile rank would you be if you were at that point right there, a z-score of 1, you were one standard deviation above the mean, that was your score. Now some of you might quickly say, oh, your percentile rank would be 70. And I'm like, well, that's incorrect. First we have to, when I say unpack the question, we have to remind ourselves what the percentile rank means, okay? Well, remember if we said the 50th percentile, that's where 50% of the scores fall at or below. And if we said the 20th percentile, that's where 20% of the scores fall at or below. In this case, I need to figure out what percentage of scores fall at this score or below it. Okay? So now I'm looking, the question I'm asking is, what percentage of the distribution is here at that line or below? So really I could shade in that entire area. Everybody with me? If you're here, what percentage of the blocks is at or below that point? Well, we know this is 70, okay? But we also have to add this area in here. And the question is, well, what is that area in there? Now we have to unpack a little bit more, because I know that the percentile rank here is 70 plus this. Well, what is this? Because I'm not going to tell you. This is figure outable. If 70% of the population is within a standard deviation, then what percentage of the population is beyond that? Well, if 70% is here, then that leaves 30% beyond one standard deviation, above and below, okay? But that 30% includes this tail and this tail. They are both symmetrical. They are both symmetrical. So it is 15% here, 15% here. How did I get that? 70% is here. So if we take that away from 100, we're left with 30, right? And then that 30% is split up into two tails. The 30% is split up into two tails. So we'll divide that by 2. So that's 15 here, 15 here. We can check ourselves, right? 15 plus 75, 15 plus 70 plus 15 is 100, okay? So if we're here, what percentage of the population is there or below? Then the answer is 85%. 70 plus 15, okay? It's figure outable. And you don't know what the answer is like this, right? It really, you have to think it through. And I am not going to be apologetic about that in a college level course. That's what we're hoping to do a lot of, so that when you're faced with a problem as a professional, you can try to figure it out even if you don't know the answer immediately. That's what professionals do, okay? So if you have a z-score of +1, then you're in the 85th percentile. Notice, folks, there's a very, very important point here. I haven't put in any values for this distribution. What I'm saying is, for any normal distribution, if you have a z-score of 1, you're in the 85th percentile. If the mean is 500 and the standard deviation is 25, and you figure out your score is a z of 1, you're in the 85th percentile. If the average is 38.5 and the standard deviation is 12.2, and you figure out that you have a z-score of 1, you're in the 85th percentile. If the average is 1,007 and the standard deviation is 203, and you calculate your x value to have a z-score of 1, you're in the 85th percentile. This is extremely important and very powerful, okay? So whether I'm talking about the basket weaver, the astrophysicist, Tiger Woods, or LeBron James, I can actually talk about their percentile rank in each of those distributions based on the z-score. I mean, we're going to get to that, okay? This is the intro to that. If you have a z-score of -1, then what is your percentile rank? Everybody get it? That would be 15, right? If you're here, we know that 15% are at this place or below, okay? And we're going to get very precise with our calculations, because this is, this is approximately we're going to get the exact value coming up, okay? But this gives us a very powerful tool because I don't care what your actual score is, your X value. If I know that you're at the 85th percentile, then I know that 85% of the people scored at your score or below. I can also say that 15% of the population scored above you, okay, if I'm at the 85th percentile. Okay, so now let's see if I can do this here. I'm going to erase these values. I'm going to go out now to a score which would look about like this, okay, which would look about like this for any distribution. And this represents a score that is the mean plus 2 standard deviations, okay? This location in the curve would represent a score that's equal to the mean minus 2 standard deviations, okay? And what I'm going to do here is now sort of shade in this entire area here, and I'm going to ask you, what do you think? What do you think that looks like? So if the whole curve is 100%, how much have I shaded in? Okay. Let me just make that tail out there like that. Okay. How much do you think I've shaded in? That is what percentage? Now, if you say 50% here, you need to think about percentages a little bit more in areas. Of the entire curve, what have I shaded in? All right. A lot more, and we know that it's more than 70%. Maybe it's 95%. Maybe it's 87%. Maybe it's 92%. You know, something like that. Those would be good guesses. As a casual kind of, you know, thumb rule kind of a thing, I would say this is approximately 95%. This is approximately 95%. Wow, that's a lot. That's a large percentage of the population. For any normal curve, about 95% of the entire population falls within 2 standard deviations. Okay, you got me again here? That is, if I say you fall within 2 standard deviations, I'm going to say, does this fall within 2 standard deviations in the mean? Yeah. Does this fall within 2 standard deviations in the mean? Yep, 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 yep. Okay, all of these scores here. All right. I could say, what do you think the percentage of the population is that falls between a z-score of -2 and a z-score of +2, right? Because this represents a score that's 2 standard deviations above the mean. This represents a score that's 2 standard deviations below. I could say that, or I could say, what is the percentage of the population that falls within 2 standard deviations of the mean? Any way you ask it, the answer here is 95% approximately. We'll get to the details, okay? We're going to get to the details. But let's think about this, okay? Let's think about this in terms of all of these blocks under here. We know what the mode for this distribution is, and that is the mode is right at the mean here, okay? That's where most people fall, right at the mode. As we move away from the mean, because the mode is the mean, in this case, the same value, we see fewer and fewer and fewer people, right? But 95% of the population falls within 2 standard deviations. What does that mean? What's the converse of that? That means that only 5% of the population falls outside of 2 standard deviations of the mean. Again, this is our first entry into sort of thinking about distributions and people and these populations. To have a score that's more than 2 standard deviations away from the mean is pretty darn rare. It only occurs 5% at a time. Most people score within 2 standard deviations of the mean. That's a fact, okay? All right, well, let's do the percentile question again. What if we found someone right here, right at this score? They have a z-score of 2. What would be their percentile rank? And let's see if we can figure this one out, okay? Let's see if we can figure this out. What would be their percentile rank if they had a z-score of +2? Everybody got it? That would include these 95%, okay? That would include these 95%, but we can't forget this tail here. We can't forget that tail. So it'd be 95% plus whatever is in this tail, and in fact, what is in that tail? Well, here's 95% between a z-score of -2 and +2. What's left over? 5%. But remember, the 5% has to be split up into 2 tails, right? This 5% is what's here and here combined, so we need to divide by 2. So 2.5% in this tail, 2.5% in this tail. So if we have a z-score of 2, our percentile rank for that z-score of 2 is 95% plus 2.5%. So this would put the person at the 97.5th percentile. Okay? Very few people, 2.5%, approximately 2.5%, fall above a z-score of 2. Very few people, okay? If we were here, if my x-score was here, my percentile rank would be what? 2.5th percentile. Approximately, okay? Yikes, what a mess. What a mess, okay? Everybody with me? Most people fall within 2 standard deviations of any mean, whether it's average height or if we talk about today's average temperature. Most temperatures fall, 95% of the temperatures will fall within 2 standard deviations of the average temperature for the day. Only 2.5 will be above that z-score of 2, and only 2.5% will be below a z-score of -2. Okay? This is one of the very powerful aspects of z-scores. We can standardize them, we can talk about percentage under the curve, and it allows us then to look at percentiles. And percentiles will tell us how many what percentage of the people fall at your score or below. Notice I didn't say anything about your actual test score or your height or the size of the fish or the temperature of the day, but I absolutely know that a z-score of 2 is going to be approximately 97.5 percentile. Okay, it's not quite that. Again, I'm going to introduce much more specificity, but this is the general concept. This is the general concept. Okay? Now, for the next portion of this video, you're going to need your textbook. Okay? You're going to need your textbook for the next portion. So if you want to pause the video at this point and go get your textbook, that would be cool. So you can pause now and go get your textbook. Okay, you got your textbook? I'm going to show you, we're going to do this much more precisely. Okay, we're going to do this much more precisely than using those approximate, the approximate symbols. So let's redo our normal curve. I think I'm going to need a new marker here soon. We'll do our normal curve. That's pretty good. Again, here's where the mean would be. We can talk about variability, and that would be the standard deviation. Once again, I'm going to try to do this fairly, accurately in terms of what it would look like. That's about 1 standard deviation away, so this is x plus 1 standard deviation. This would be x minus 1 standard deviation. So this would be a z-score of 1. And by the way, I hope nobody is saying, why would that be a z-score of 1? Because that would indicate to me that you forgot the concept of the z-score. You can't forget that. This is a cumulative course. The z-score tells me how many standard deviations away from the mean I am. Z-score tells me how many standard deviations away. If I'm above the mean by 1 standard deviation, then my z-score is 1. And down here, my z-score is minus 1. Okay. So we said that it's approximately 70%. If I look at this area underneath the curve, that is the percentage of blocks underneath this part of the curve, I said it's about 70. Well, we're going to get a little bit more precise than that, and I'm going to ask you to open up your book to the back of the book to Appendix B. Looks something like that, okay, Appendix B, and this is our statistical table. It's called the unit normal table, all right, Appendix B. And I happen to I have an enlargement of that. But let me show you how this works. Whenever we have a distribution and we locate a spot on that distribution, okay, so here's where we're at, okay, we have a smaller portion of the curve here, and we have a larger portion here, okay? This is just like a dog, okay? The larger portion is referred to as the body, and the smaller portion is referred to as the tail. The only time we're not going to have a larger and smaller portion is if we went right down the middle, right? But we already know if we go right down the middle, then we have 50% here and 50% here, right? Because it's symmetrical. It also represents the 50th percentile. It's the median, blah, blah, blah. We've been through all of that, okay? Any other portion or any other position on the curve will give us a larger and a smaller portion. And it's not always in this direction. If we were, for example, talking about a score down here, then this would be the body of the graph. This would be the tail of the graph. Okay. So, big deal. So what, right? Well, if we look at our unit normal table, what we will see is a list in column A, and I want you to take a look at that. In column A, it will give you all sorts of z-scores from 0, 0.1, 0.2, 0.3, 0.4, 0.5, 0.8, 1.2, 2.1, all the way through. It'll give you values for the z-score. And let me show you a kind of a segment of that table like this, okay? So here are potential z-scores. And what they will show you is for this z-score, for a z-score of 0.97, for example, they'll tell you what proportion of the curve is in the body and what proportion is in the tail, okay, for a z-score of 0.97. For a z-score of 1.03, this is the proportion in the body, this is the proportion in the tail. Now, I'm going to typically ask you about percentages. Most z-scores are given as proportions because people know that proportion and percentage are really the same thing. It depends on where you put your decimal place. So this could be read as 83.40%. This is 16.60%. Okay. Now what you will notice, or what you should notice, or what I'm going to ask you to notice, is that if we add the body to the tail, what do we get? The whole dog. Okay? That is, each of these pairs, if we add them together, will add up to 1, or 100%. 83.40 plus 16.60 is equal to 1.00. 83.4% plus 16.6% is equal to 100%. The body and the tail make up the whole dog. There's nothing left over and there's nothing short. Okay? So that's how these columns work. In fact, really, you could just report the proportion in the body, because people should know that the proportion in the tail is just 100 minus this percentage, right? So anyway, so if we use this table, this z-score table, remember the question is, what percentage of the curve falls within a standard deviation? So +1 and -1 for z-score. By the way, I don't want to forget to say this, you won't see any negatives in the z-score table, in that unit normal table. The reason for that is this is a symmetrical curve, and so whatever value we see for +1, the same value is going to be used for -1. If we had a score here, then this would be the body and this would be the tail. If we had a score here, this would be the body and this would be the tail, okay? But the values would be equal. All right, so big deal. Let's see how this table works. What do I want to know? I want to know this area here, okay? There's a couple of different ways that I can do this, and I'll show you the different ways. For now, I'm going to suggest that you do this. I want this area here, okay? But this is neither a tail nor a body, right? Because this would be the whole body. Then this is the tail, right? But I don't want this. I want this right here. So here's what I'm going to do. Well, I can figure out how much is in the tail here if I look at the table, the z-score table. Okay. Here's a z-score of 1. How much is in the tail for a z-score of 1? Well, I'm going to go over. I'm going to report this as a percentage, okay? I am typically going to ask you for percentages. So it's 15.87%. 15, I will use a different marker in the next video. 15.87% in that tail. Now, like I said, this is a symmetrical curve, and so if I go down to a z-score of -1, I get the same percentage here, 15.87%. Okay, let's check that again, right? Here's z-score of 1. I'm going to go across 0.1587, that's 15.87%. Please make sure you look at that table, because I'm going to be asking you questions on the homework and on the exam to answer questions like this, of course, and so you'll need to familiarize yourself with the table. Okay? So, well, I have those two tails, but Dr. Speck, you want us to get this area here. Well, guess what we're going to do? We're going to take the whole dog here, that is 100%. Okay, that's the whole curve. And I'm just going to lop off these tails. By lopping off, I mean, let's subtract them from 100. Okay. And what do we get? Well, we'll get what is left over here in this portion. It's very physical. It's very concrete in a way. We have this whole curve. We don't want this. We don't want this. And so what's left over? 100% minus 15.87 minus 15.87. So what's left over? 68.26%. Okay. Remember, we said it was about 70%, approximately 70%. And as you move forward, that's a casual value that you can think. 70% of the population falls within a standard deviation. But more technically and specifically, it's 68.26. So that's what we're going to do in this class, for sure. Okay? Let's do the same thing. Oh, and by the way, so let's be more precise with our percentile rank. So if somebody had this score right here, their z-score was 1.0, what would be their percentile rank? Well, that means how many people scored at that score or below it, all the way below it. So in that case, I'm going to do 68.26 plus 15.87, because we need to now, if I'm asking about percentiles, this is a different question, right? 68.26 is in here. If I'm asking percentiles, I want here and everything below it. So let's do this. 68.26 plus 15.87. So my percentile rank would actually be 84.13%. Okay, that's the percentile rank. Okay. This all comes together like puzzle pieces, right? We have the whole puzzle. Now we can start chipping away and getting portions of the puzzle. So let's do the same thing now for a z-score of 2. Let's do the same thing now for a z-score of 2. That is, if I'm out here at a z-score of 2, which means I'm 2 standard deviations away from the mean. Another way I can say that is to say that, oh, sorry, folks. Okay. So now I can say what percentage of the population falls within 2 standard deviations of the mean. Again, I mentioned that it's about 95%, but as students taking a statistics class, we don't want to do an about, we don't want to be approximate. Let's get more specific. So we're going to look at our z-score table, and we're going to look for a z-score of 2, and you have to go through a couple of pages. And here's kind of a blow up of that, okay? So I'm looking down, looking down, looking down. Here's a z-score of 2. If I had a z-score of 2 here, it's telling me 97%, 97.72 is in the body, and 2.228% is in the tail. Okay, everybody with me? Look for 2. There's the body, there's the tail. Now I'm going to go back to the question. So this is neither body nor tail. But if I get this tail, 2.28, and I get this tail, 2.28, okay, then I can figure out what's in here, of course. So minus 2.28 minus 2.28, okay? Let me get my handy dandy here. So 100 minus 2.28 equals minus 2.28 equals. So it'll be 95.44%. So that's good. I mean, we said approximately 95, but 95.44% is the actual percentage that's between a z-score of -2 and a z-score of +2. Again, another way I can say this is 95.44% of the population falls within 2 standard deviations. Okay, within 2 standard deviations. And just to be complete here, let's talk about the percentile rank. For somebody that's here, what is their percentile rank? Right there. Okay. For someone who's here, what is their percentile rank? Well, we need to go. We're asking what percentage of the population is at this point and anything below it. So that means 95.44 plus 2.28. Okay. And that gives us, let me do this with a calculator, even though I should be able to do that easily without one. Let's be precise. 97.72. That's the percentile that they're at, which means less than 2% of the people, less than 3% of the people scored above. If you have a z-score of 2 on an exam, or if you have a z-score of 2 at the track meet, or if you have a z-score of 2 with how much money you made this year, you're out there, man. Like, you are way out. You're high percentile. And I haven't even put in the X values. I'm just talking about your z-score. And that is the power of z-score. And we're going to be doing tons of these problems, tons of these questions. This sets us up to do inferential statistics. Okay? So again, cumulative, cumulative, cumulative. If you have questions at any time, please do not hesitate to drop me an email. And maybe I can answer email. Maybe we can Zoom. However it is, we can address your questions. But this video is extremely important for moving forward, and make sure you're comfortable looking at that z-score table as well, because we're going to be using it quite a bit actually in the lectures to come.